live now, so we're good
great.
to go.
Great. So welcome to everybody to this 7th talk of the Women in Logic series. So Women in Logic, just to remind you, aims to promote a forum that brings together women working around logic, from foundations of computer science to philosophy, including mathematical logic, logics in AI, and logical approaches to language. So this is already the 7th talk of the series, and all the talks are organized by the Vienna Center for Logic and Algorithm, which is a center funded by the Vienna University of Technology with the aim of promote research and outreach in logic and algorithm. So I'm very happy and honored to have today Nina Gierasimczuk, sorry for my pronunciation, and Josephine will introduce her.
Yes, thank you very much, Agatha, and thank you very much, Nina, for accepting our invitation. Nina Gierasimczuk is an associate professor at the Department of Applied Mathematics and Computer Science at the Technical University of Denmark, DTU. Before she was employed at the Institute for Logic, Language and Computation at the University of Amsterdam and the Bernoulli Institute of Mathematics, Computer Science and Artificial Intelligence at the University of Groningen. At present, she serves on the board of the European Association for Logic, Language and Information and the Scandinavian Logic Society. She is also a member of the steering committee of the DALI workshop and the NMR workshop, and an associate editor of the Journal of Logic, Language and Information, Annals of Mathematics and Artificial Intelligence, Fundamenta Informatica, and Nordic Machine Intelligence. Her main research interest lies in the logical aspects of learning in both single and multi-agent context, and involves knowledge representation, dynamic modal logic, computability theory, belief revision, and multi-agent systems. She's also studying the role of logic and logical modeling in cognitive science. Again, thank you for accepting our invitation. For the talk, well, Nina will kind of give her talk, and then during the talk, you can already add the questions to the Q&A, but only at the end of the talk. We will go over them. I will read them out loud while Nina answers them. Thank you very much for being here. Nina, take it away.
Thank you very much. Can you hear me okay? Yeah? Okay, great. So indeed, I will take questions after the talk because it's a bit tricky to navigate the situation here with all the little windows. Okay, so today I would like to tell you a little bit about a quite broad research agenda that I've been pursuing for a while in my scientific life, roughly since my PhD in 2010. So it's been a while. Of course, it's not the only topic that I study, but somehow it grew and it has several different branches and connects to other things that people are interested in. So I will not only talk about my own work, but I will also mention some relevant, interesting topics just to bridge and connect to other people's work. Before I start, I would like to say that I'm very, very grateful for this invitation, and I've been supporting Women in Logic maybe a little bit too quietly because I'm not very active on social media, but I'm very supportive of the initiative, and I'm very, very proud to be part of it now. Okay, so the topic of this lecture is belief revision, and I will start with that. So forgive the initial, a little bit pedagogical perhaps, angle. So I will try to show you some examples and maybe make you a little bit more familiar with the setting, because as much as all of us are logicians, maybe not everybody had to do with belief revision itself, especially that it sounds a little bit soft. Beliefs and revision, it's maybe not a very normative way of thinking about things. So people are usually skeptical, but I would like to just show you what it's all about. And then I will move on to my work in which I try to relate belief revision with learning. And it will happen in 2 steps. The first one will be a little bit more abstract. The second one, belief revision and learning. The third chapter will be a little bit more constructive. And then I will, as I promised in my abstract, I will relate to some existing topics that are very connected to what I do. So Let's start with belief revision. So the problem of belief revision was already foreshadowed quite early before the official start of the belief revision research happened. And it can be actually linked to the issues related to database, especially databases, especially the dynamic type of databases. So whenever we want to have a database of some facts, we would like to be open to revise it, right? Because I mean, things can change, right? Like information can come to the database, and we would like to maybe somehow maintain the consistency of the overall representation while including the new information. And as long as this database is somehow of stuff that is disconnected, it's just very easy to drop new things into it. But as soon as there is some internal consistency that we have to make sure holds, then updating a database becomes slightly more challenging because you have to maintain the internal relationships while you put in the new information. So, of course, this perspective is not only relevant for databases and computer science, but it's also relevant for other fields that are traditionally related to logic, like, for instance, philosophy of science, where we want to look at how scientific theories perhaps get revised in light of new information and new data. And also, a little bit more cognitively or epistemologically speaking, it also has to do with the change of our beliefs, subjective, perhaps, representations of the world that we have in our heads, or AI has in its little, whatever it has there, cloud. Then when there is the new information, then we would like to update it, perhaps satisfying some conditions of rationality. And here the rationality is this keyword, right? So what does it mean to be rational about revision? Of course, we would like to maintain some logical properties. That's what belief revision studies. And what Gardenfors himself would say about this motivation? Well, he wrote as follows. So belief revision is a topic of much interest in theoretical computer science and logic, and it forms a central problem in research into artificial intelligence. In simple terms, how do you update a database of knowledge in the light of new information? What if the new information is in conflict with something that was previously held to be true? So here we can see the central question, right? So the conflict, the clash of what we believed and what comes in. I think this topic is extremely pertinent these days when we look around and we see people changing their beliefs or maintaining certain beliefs, and we would like to maybe interact with them. It's very hard to overcome that clash and conflict. So traditionally, belief revision handles this problem. The most prominent setup in belief revision is the so-called AGM modeling of belief revision. AGM comes from these three names, Altron, Gardenfors, and Makinson. They published a paper together in 1985 in the Journal of Symbolic Logic. And well, in a way, this is seen as a starting point of belief revision theory, right? So since then, we have a lot of research on the topic because they proposed certain interesting rationality postulates to which I will get soon. So the belief representation in the AGM framework is very simple. First of all, we are talking about beliefs rather than knowledge, even though very often we will talk about knowledge bases and presence of knowledge in such systems, only because beliefs are kind of more changeable, right? They have this possibility that they might be false. Knowledge has a little bit of this normative component. When you say somebody knows something, it usually implies that it must be true, or there is some sort of weight to that belief. But here we will use beliefs as this type of qualifying term that allows us for the state to be changeable. So simply speaking, a belief will be a sentence in some formal language, and the whole of the beliefs of an agent at a given time, of course, will be set of such sentences. That's very simple. And in particular, AGM would traditionally treat it with propositional logic. So we would represent every belief as a propositional logic sentence and then put them in a set to form the particular set of beliefs at a given time point. An important thing to consider when thinking about beliefs is the consequences of what we explicitly believe. So for instance, a couple of examples. If I believe both that John is a bachelor and John is handsome, then I might also believe in the conjunction. I should probably also be committed to believe the conjunction of these two elements, right? So, well, using natural language, yeah, I could even say that John is a handsome bachelor. More complex situations, if I believe that if we charge high fees for university, only the rich enroll, and I also believe that we charge high fees for the university, then I'm somehow committed to also believe the consequence of it, the fact that only the rich enroll. Right? Of course, things can become a little bit more tricky. For instance, if I believe that the barber is male and the barber shaves only those men in town who do not shave themselves, I might come to believe whatever. So, here we are playing a little bit with the possibility of having inconsistent beliefs, and that's something that we would like at a given time point to avoid at all cost, because if our beliefs are inconsistent, we have this explosion that we suddenly start believing anything, right? So that's why we would like to maintain the consistency of beliefs at each time point. However, of course, when the new belief comes in or new information comes in, it might be contradictory to what we hold dear in our belief system. And so we should somehow revise this set of information to maintain consistency. This is a tiny, tiny definition on this slide. Sorry about that. But just to set the stage, I will use the consequence operator to denote the set of the logical consequences of a certain set of formulas. Okay? So this will be, this won't go very far, but so we will assume that belief sets that we will be talking about in this talk, they are deductively closed in propositional logic. Right? Belief bases are taken to be this kind of finite fragments, something that generates the belief set, so it's open towards the consequence. However, the belief bases are this kind of like just stuff that we explicitly believe. Belief sets are this belief bases closed on consequence. From a logical perspective, these belief sets are kind of interesting because they are more abstract. Right? So I will focus on them. But of course, belief bases are definitely an interesting topic of discussion in belief revision, and they've been so since a long time. So, okay, so some small exercises just for you to realize the intricacies of this framework. So let's take Bob, because why not? Bob will be our agent, and Bob believes consequences of the belief base, the set consisting of P and Q. Okay. And then he learns from a reliable source that not Q. So here we are giving the priority to the input. The not Q is the case. Now Bob has to change the belief, right? So maybe you can quite easily try to compute that. Well, here the answer is relatively simple. Probably we would like Bob to believe, after this information comes in, the consequences of the simple belief base in which Q was replaced with not Q. And, there was quite a lot maintained from the previous belief because P still holds. But the belief base was maintained so that this contradiction between Q and not Q was removed. Right? So that would be maybe a solution to this problem. Well, let's look at a more complex example. We have PQR. That's something that Bob believes to start with. And then somebody tells them it's not the case that Q or R. Right? And well, now we have to do maybe a little bit more computing. We have to see which of the sentences that Bob's beliefs are perhaps inconsistent with this incoming information. And then we want to remove them and add this new information. Right? So on a purely syntactic level, we could take simply P and not Q or R, right? As the new belief set, the consequences of all of this. So far, so good, pretty simple. We could already argue about a couple of things. I'm pretty sure there are some questions about this already, but okay, that's acceptable. But some situations are much more complicated. So let's consider this simple situation. Bob believes P and Q, and he also believes that P implies Q. Now, from a reliable source, he learns that not Q. Right? What should the result of this update be? Normally, what I do is that when I teach belief revision in my Introduction to AI course, I actually ask the students to solve this by voting. So I give them a couple of options to decide what would be the outcome of such a situation. And I want to just show you what happened last year in the last test. So I had just 98. I have 300 students in the course, but only some of them are awake. So I don't know if you can see this here. Josephine, can you see it? Because I can see your face. Yeah, you can see it. So here are the answers that my students gave. They are students that are familiar with basic propositional logic. So some of them would still output quite a lot of different things. Well, the only thing that didn't get voted is that nothing has, oh no, there was something here. So maintaining P and P implies Q because Q would follow. So we want to accept not Q, that's not an option. Let me put this little picture here so it fits within the whole, yeah. But you can see that the option D and F, they are actually both quite highly appreciated by the students, and this is no accident. So both of these options are actually sensible outcomes of, oh, is it really? Maybe they voted something wrong. In any case, B and D are the possible outcomes of this situation, right? So we would like to remove the inconsistency with not Q, and we can do it by either dropping the P, because then we have Q and P implies Q. So we can drop the implication towards the Q in two possible ways, right? One of them is that we accept not Q and maintain the implication, and the other one is that we accept not Q and maintain the antecedent of the implication, but we drop the rest. So as you can see, there are different ways in which possibly we could update a belief set when the new information comes in, right? So there is already quite some choice to make. And the question is, oh, is one of them more rational than the other? Are there any other things that interact with these decisions? And in order to see that maybe clearer, I would like to show you another representation of the belief revision process that is on plausibility orders. So instead of thinking about beliefs as sets of formulas, we can think about possible worlds being possible valuations over a set of propositions. In this case, a very small finite set of two propositions, P and Q. We have all possible valuations listed in our columns. And then each of these evaluations codes a possible world. Right, and then this representation is common in belief revision literature, so that's why I'm using it here as an introduction. The lower in this table the symbol is, the more plausible the world. So here the name X refers to the possible world in which P and Q is true. The letter Y corresponds to P and not Q, Z to not P and Q, and so on. Right, so this plausibility representation allows us to see how the agent relatively values different possible worlds. So in both of these representations of plausibility, we actually get that the best world in both of these cases is the world X, which makes both P and Q true. And it is actually a world that is consistent with the set of beliefs that the agent holds, right? So P is true and Q is true, and P implies that Q is true, of course, because it's a consequence of that. However, what you can see is that these rest of the worlds, they are ordered in a different way. So on the left-hand side, the next world, the next best world is Z, and in the other case is the W. right? So the agents not only select their favorite words as their belief at a given time, but they also somehow code the propensity to change. So what would be the next best possible world? And we can see that, of course, this will have implications on the revision process. Because if we just think about this example that I just gave quickly a second ago, if our agent that had the X as the best possible world in both cases actually received the not Q as the incoming information, and they will try to find the best possible world according to their plausibility that satisfies this not Q, the results will be different depending on which plausibility order they actually assumed, right? The next question is, okay, I accepted the not Q, I would like Y in the case on the left or W in the case of the right to be my new best world. But the question is, what do I do with the rest of the structure? Do I actually maintain the rest, or should I maybe rearrange everything somehow? How much do I cherish my original plausibility order, my prior, as we call it? So all of these questions are actually very relevant. Sorry, there's some skipping going on for our revision process. Okay, so just to clarify, we were talking about sets of formulas as beliefs. They are equivalent ways to look at the belief revision process with possible worlds, just as we do here. The transition is a little bit tricky between the two worlds, but it's possible to do. Now, how much learning is going on in this setup? That's the question that I would like to ask. So when we look at the traditionally accepted AGM postulates, so the postulates that were formulated in that seminal paper, we see a couple of very interesting desiderata that are supposed to say something about the rationality of the process. In particular, the second condition here is the so-called success postulate that tells us that when we revise with phi, so this is the revision operator, our belief set gets to be revised with the formula phi, then phi is believed. So phi becomes part of that revised set, which is learning, right? So the condition here is that, okay, I received phi from a reliable source. So then when I do whatever I do there in my little space, I actually end up accepting phi. So even if I didn't before, now I do. There is this change. And you can see it as learning, right? There was possibly not phi before, now it's phi. But what I want to say about this is that this is a very minimal requirement and also not even completely valid always, because it also depends on where the information comes from. Maybe you cannot trust it. Maybe you just want to trust it a little bit. Sometimes all sorts of things can happen when the information comes in. But even if you assume that the source is super reliable, there still remains a question, isn't there more to learning than just accepting what you hear? And the rest of the talk will be focused on that question. How to see a learning process as an iterated belief revision policy. But before we get to that, I would like to explain a little bit about my basic setup so that we all know how things go. So I already showed you two ways of representing this belief set. So one with just sets of formulas, the other one with plausibility orders in the nice little tables. Here I'm going to switch the picture yet another time to a different representation in which we will think of an epistemic space that consists of possible worlds, S, T, U, and W. And those possible worlds are possible valuations. You can think of them this way. They are like possible worlds, you would take them to be in modal logic. And on top of that, I want to define observables. So you can think of them as propositions that are true at a given possible world. So for instance, the possible world S would make the observation O1 true, but it wouldn't make O2 true, right? Because simply the possible world is not an element of that observable. What you can see about this example is that also T and U, they have exactly the same observables true in them, both satisfy O1 and O2, and so they are not distinguishable between each other, which is very annoying if you want to identify in which world you are, given the observations that you can receive in them, right? And this will be our question. Can we learn which possible world we are in, so which propositional valuation, for instance, is the case, given the information that we are getting about that world? In particular, that can be expressed in propositional language, right? It can be expressed as just simple observables that are true in them, or some combination of observables. So as you can see, this little picture allows us to extend it arbitrarily in a quite easy way, because we would like to potentially also treat infinite cases. Cases where, for instance, we have an infinitary language, so we have infinitely many propositions to deal with, possibly because our world is always expanding, or because we want to maintain that there will be always, that new observations are always possible, right? This could happen. So here, both of the O, the set of observables, and our states are at most countable. That will be our assumption. Okay. So now the question would be, okay, so abstracting away from belief revision policies, just in general, if I have some uncertainty range that is coded by these possible worlds, and there are some observables that are possible to see in different worlds, they will, depending on the space, we will be able to distinguish between the worlds to a different extent. Right? So for instance, as I mentioned before, in our initial epistemic space, the worlds T and U are impossible to distinguish. You will never be able to learn whether you are in T or in U because they make the same observables true. So maybe a goal would be to find out if there is perhaps some observable about U and T that would distinguish it between each other. But in general, we would say that these two, these four states form a space that is not separable, because T and U are not separable by observations. Some spaces will be better in this respect. So for instance, here on the left, the picture B, we will see an example of a space that is weakly separated. So S is separated from T by the observation V, because V is an observation that I can see in S that cannot see in T, but T is not separated from S. There is nothing that I can see in T that I cannot see in S, because U is the only thing that I can see in T, and I can also see it in S. So they can be distinguishable, separable one way, but not the other. Some of you that are still following me might say, oh, what about negations? Maybe I can see not V, but we are not closed on negations. We don't have that yet. Okay, and the most friendly condition for learning the identity of the actual world is the strongly separated case, in which we have two possible worlds in this particular case, and each of them has an observable that distinguishes it from everything else, right? So if I see V, I know that I'm in T, not in S. The same for S. There is an observation U that I can see, and it will isolate me from the other one. This particular situation in the picture C, this corresponds to the maybe easiest way to think about learning, which is this kind of learning with certainty. That I can actually expect a situation in which I will know for sure where I am at a given point in time. As soon as there is some observation that I can get at a given time, that will allow me to say I am in this possible world, but not in any of the other ones. But as we can see in the picture B, this doesn't always happen. Okay, so we would like to see how far we can push the notion of learning in this context. So again, the question is, I'm faced with some uncertainty, space, possible worlds that make certain propositions true. My goal is to know which possible world am I in? So that's the question that I want to answer. In order to address this, we need a couple of notions. So first of all, we need the notion of data stream. That is something that we are learning from. So given my space, I will take a data stream to be an infinite, open-ended sequence of observations that I can get about the space. A data sequence will be just a finite fragment of that. Now, given an epistemic space and a state from that space, I will say that a data stream is sound with respect to the state S if every element listed in the sequence is true in S, and complete the other way around if every observable true in S is listed in my stream. So sound and complete data streams are simply this type of very friendly conditions for learning, in which I in fact sit in one possible world and I receive all and only true information about that world. And the goal would be to be able to guess which world I am actually in, right? So over time, you might change your mind about the identity of the world, but you want to converge to the right answer. Okay. So that's why we define the notion of a learner. Learner is a function L that on an input of the epistemic space and some finite initial segment of the data stream outputs a set of possible words that we call a conjecture. So it basically says, okay, I know what is the uncertainty space, I know how to deal with my observables, and now I've seen a certain amount of data, and now my guess is that I am maybe in this possible world or this or this. So I restrict the space a little bit. Maybe I was able to eliminate some possibilities. Now I know that I'm getting more and more information about the identity of the actual world. Now, the notion of learnability that we want to study here is as follows. So we will say that an epistemic space is learnable by a particular learning function if independently in which possible world you are. So for every state in my space, and then also every sound and complete data stream for that state, there is a finite point in time, n, from that moment, so for all the next steps after, I am right about where I am. So the learner truthfully answers with the singleton of the actual world. So the idea is that maybe you don't know for sure where you are, but from some point on, your plausibility or whatever, your space, your conjecture stabilizes on the true answer. This is what we call this learnability. It's also called identifiability in the limit, because we have this limit behavior that the answer converges to the true prescribed answer. And in general, we will say that a space is learnable if there exists a learner that learns it. There are some examples, famous examples of learnable spaces and unlearnable spaces. For instance, this is a good example. We have this interesting case in which S makes infinitely many, countably many observations true. So in S0, we have O0, O1, or 2, or 3, and so on. Then S1 makes O1, O2, or 3, and so on without O0 true. So they correspond to, each of these points correspond to natural numbers without some initial finite fragment of them, right? So this would be a world that makes all natural numbers true, 0, 1, 2, 3. This one would make 1, 2, 3, but not 0. This one would make 2, 3, 4, but not 0, 1, and so on. And this space is learnable in our sense. So let us see what happens. So we are an agent, we are faced with this really quite dramatic uncertainty, but we know if a certain possible world is the case, we know what we will observe in it. So let's say that we observe O2. Then since we assume that the data is sound and complete, so it comes very easily to us, we can see that we can exclude S4, S5, and so on from our space. So these are the worlds that cannot be the case, but we still have some uncertainty regarding the true identity of the actual world. And since our goal is to identify the world exactly, we shouldn't be answering with this whole set, but rather make a bet which one of these worlds is the actual one. And there will be different effects depending on what we decide to do. This wouldn't be a good idea because this hypothesis is overgeneralizing. So it makes not only O2 true, but it makes also O0 and O1 true. So we are kind of maybe making the more general assumption that we should. Instead, it would be prudent to guess S2 and then wait for other information that will allow us to falsify that state. So if it's not the case, if S2 is not the case, we will observe either O1 or O0 that will tell us how to change our mind. But if we never receive the observation that contradicts what we've done so far, we can stick to S2 forever and we will have identified that world in the limit. So here comes the difference between learning with certainty and learning in the limit. This allows us to stabilize to the correct answer. There are examples of unlearnable spaces, so not everything is learnable in the limit. And maybe for this talk, that's enough to know. I'm very happy to answer a question about this if somebody wants to see an example of a space that is not learnable. It is a restrictive notion. Now, what does logic have to say about it? Well, so far we have managed in the team together with Aleksandru Baltak and Sonia Smets, we've managed to connect this notion of learnability to topology. And we found it's published in our TARCS contribution from 2015, that an epistemic space is identifiable in the limit if it's the so-called if it generates the so-called TD topological space. For those of you that are interested in topology, this might be an interesting fact. So here is the reference for that. Moreover, for those of you that are into topological semantics, you can ask, okay, does it have anything to do then with logic, with, let's say, topological logic, topologic? And yes, we also have recently developed modal logic, dynamic modal logic of this phenomenon of learnability using, instead of Kripke semantics for knowledge, using topological semantics that takes these observables as open sets to interpret the box. This is just a slide to show you where this research went. In case you're interested, you can just open these papers and have a look at the consequences of this modeling. But now, having said all that, having set the stage for learnability, I would like to now know how to link back to belief revision. So is there a sensible way to think about certain belief revision policies? So how I treat the incoming information according to some rationality postulates, and whether or not these belief revision policies are truth conducive. So if I map the notion of a belief revision to my notion of learning, will I actually be able to identify the real state, the actual state of affairs, or not? Right, and this is the question that we've asked in this work. So it seems on the surface that this notion of learning, meaning identifying the actual world from observations and belief revision, revising the belief just constructively, they are somehow separated. But now we would like to ask, okay, how does this incremental way of changing your mind in belief revision, how does it fare with respect to this long-term horizon of the true state, the right belief, the correct belief about the world, assuming that there is one, right? So in this sense, I am a little bit Tarskian. I still believe in the truth, objective truth. So the truth exists in my setup, and yeah, it's just arbitrarily defined, but yeah. Yeah, so that's the motivation. Of course, the motivation has also some philosophical depth. Why would we want to look at this type of revision? There are motivations in computational learning theory classically that use Gödel numberings for hypotheses, and then we are following some sort of prescribed order of hypotheses as we learn a certain concept. But in philosophy of science, there is also this notion of Occam's razor, which also says something about, okay, there's some plausibility to hypothesis, and when you change your mind, you should follow it, because otherwise you might overlook the truth somewhere on the way if you make your theories too well, baroque or too general. So there is some interesting motivation going on in the background. Okay. So now in order to talk about a belief revision, as you remember my little tables with plausibilities, we would like to have some order on possible worlds. And in my setting, this will be introduced as this plausibility pre-order on possible worlds. So as before, we have possible worlds, observables, and some order on our possible worlds. And it enriches our previous epistemic space. So now, maybe this is not very important for this particular talk, but maybe it's important to note that because we allow these spaces to be infinite, sometimes you might have spaces that are not well-founded. So in the sense that this plausibility order will not always point you to the best possible world. So there could be an infinitely decreasing or infinitely increasing plausibility. So it would be hard to find the minimum, impossible actually. So in this case, we are defining some interesting notion of belief that is a generalization of the usual way of thinking about the belief operator. This is for those of you who know a little bit about belief revision to kind of understand how this generalization would work. Okay, so now what we want to do, we want to study a belief revision operator that works in the following way. It takes our plausibility space, BS, it takes an observation, and it outputs a new revised plausibility space. And it can be iterated. That should be also known. So we can iterate this operation, giving the agent or the revision method more and more observations, and constructively seeing at each step what comes out of that update, right? And now the idea is that this belief revision method can serve as an engine for learning. So now we would like to set these poor belief revision methods in our general setup of learning and give them true, like the sound and complete streams one by one and see how well they do. So see if they actually, even on this super friendly situation on learning, they actually behave well. So they converge in the limit to the true state of affairs. Traditionally, taking it from a super symbolic perspective, there could be three ways of looking at belief revision. One is conditioning. That's a very hardcore version of learning, in which whenever we see an observation, we simply delete all the states that are inconsistent with that observation. So it's like very hard learning. I see P, I remove everything that satisfies not P from my space, right? Think about it. This is super strong. It doesn't allow forgetting the information. When you learn something, you learn it forever. There is no way back. Then there is the lexicographic upgrade. And the lexicographic upgrade is quite general. So here you can see a little video in the interest of time. P comes in, everything that satisfies P becomes overall better than everything that does not. So here P, they go to the front, but they preserve the internal plausibility between each other, right? This is a super strong way of learning because you really update your whole space, but you still preserve the old states. Just in case, if something went wrong, if the information was false, there is some way of recovering perhaps the old space. So it's weaker than conditioning in this sense. Exit lexicographic and enter minimal. So by minimal upgrade, I mean something that is very popular in belief revision literature. I only make the best of possible world satisfying the information better than everything else. And the rest remains the same. So you might see it as a little bit of a lazy way of updating. So I don't go through all the space, but instead I pick the best one and I put it to be better than others, right? This video is a little bit, animation is a little bit naive. Of course, there could be a lot of messy things going on. And when you actually try to define it, it's a little bit tiresome because you have to maintain the orders and pick the minimums and things like that. But I mean, conceptually, it's very simple. And it also traditionally in belief revision literature is seen to have many advantages because it actually preserves some underlying hidden belief structure quite well. So now what we did in the work that I want to describe quickly is that we checked how these methods fare on in this setup when we give it sound and complete information streams. And we can see that on positive streams, so the ones that I just described, minimal revision is by no means a good method. So even though it's computationally efficient and it has all sorts of traditionally recognized features, it actually does not fare well as a learning method. It will fail. The argument is quite simple. I will share these slides later and also give you the link to the paper. You can have a look at the proof, but the gist of it is that it's simply impossible to find an appropriate plausibility preorder that would allow us to avoid the sort of loops, the circularity in the space, and without digging deep enough into the space of possibilities. Now, minimal revision is not universal. Conditional lexicographic are, so they are good learning methods, provided that you have all information, the sound and complete information about the world. However, none of these methods are universal when you require that the plausibility must be actually well-founded. And that's maybe another message to the belief revision community that is somehow negative from this work, is that in the belief revision community, in the literature, it's usually assumed that you can find the minimum, that the plausibility order is always well-founded. So there is something that is the best world according to the agent and you can stick belief on it. But if we assume that, then we actually will, by necessity, lose some of the learning power of our universal learning methods. And our example, the concentric circle example from before, is one such case, in which initially, in order to learn that space, it was required that in the first step, the plausibility became better and better infinitely to the right. And only when we saw the first observation, we were able to cut off this infinite tail and focus on the best according to the new data. Again, the proofs are in the paper. I encourage you to look at that. Then from a logical perspective, the next question is, what happens if we close our observations on negations that corresponds to learning from positive and negative data or supervised learning? Then you can see that if we close on negation, then actually we are able to model so-called fair streams. that allow some finite number of errors and then recover from them in the sequel, in the rest of the stream. That can happen if we have noise in data or we have lying agents, and sometimes the information comes in it's false. So then, of course, under this situation, conditioning will not be a good learning method because conditioning simply removes all the states inconsistent with incoming information. If somebody lies to us and we remove, we cannot recover. So then lexicographic revision is a good method, but minimal revision stays still bad for all of these conditions. So now I'm almost finished. I started a little bit later, so I'm stealing 5 more minutes. But I would like to tell you a little bit more about the possible extensions and what's been happening, because so far this work is extremely abstract. We are starting from belief revision, and we are talking about to some of you, maybe obscure notion of learning. So what is it really, like some convergence to the true hypothesis? Yeah, recently some ways opened in which we can actually see neural network updates or learning as a sort of iterated belief revision process. This is not my work, but the work refers to my work. So I feel allowed to talk a little bit about it because it actually connects very well with what I described so far. So the idea of a neural network is that we have certain number of layers, and we have the input layer in which some activation happens from the input. So it could be, for instance, a black and white image. We have certain pixels that maybe fire up. Then this activation is propagated to the next layers. And finally, because we are doing logic, we want to assume that our networks will be binary. So we will, when we have the output, we will also assume that there is a certain threshold tau for each of the outputs of our neural network that says whether or not the output is 0 or 1 for each of these output neurons. Right? So for those of you who are familiar with neural networks, this should be pretty easy to grasp. For those of you who are not, again, the reference to the paper is there in the slides. But now, if you think about it, such a binary neural network, what it does is that it transforms the binary input and the input layer into some set of binary outputs. Right? So depending on the configuration of zeros and ones in the input, we can have for each of these outputs 0 or 1. Of course, the propagation goes here through the network, and it follows certain number of thresholds and activation functions. So there's a lot hidden there. But on the outside, when you look at it, it simply looks as a truth function, right? So depending on the zeros and ones on this level, we get zeros or one for each of the output neurons. Right? So each of such activations can be seen as a propositional formula simply, right? So the output, binary output neuron Y is a function of the binary input neurons from 1 to n in this case. So then if we think about it, we can actually simply take this formula to be our knowledge or belief set, right? So we can simply see it as a propositional formula and treat it as a state of belief, especially that, of course, in the general case, there will be several outputs. So for each of the outputs, we have a separate formula, and we want to satisfy the set of such formulas. Our network satisfies a set of such formulas. So now, very nicely, as a result, we get simply that our neural network, binary neural network, can be represented as a bunch of belief sets, which in my lingo would be an epistemic space, right? So that's how you could do it. That's how you could see a particular configuration of a neural network as a propositional formula. Now, what training in artificial neural network does is that it iteratively tunes the parameters in order to minimize the disparity between the desired actual outputs and the predictions of the network, so to improve its predictive accuracy. So when we do the forward propagation, the input propagates according to the weights through the network. When we do the back propagation, computing the gradient of the loss function is happening that is relative to each parameter. So now what's been done in this particular paper that I want to tell you about by Theophanis Arafanis from Greece, it was published this year, actually I think August the paper came out, so very recently, last month. You can actually see that what can be done is simply seeing the individual states of the neural networks as the learning happens, as a sort of transition between different states of the knowledge base, of the knowledge, belief set, right? So we have a belief set that is coded by a certain formula, and then as the learning goes on, this particular knowledge, belief set changes over time. So we have a sequence of belief sets. And then what we would really like to happen is that this KN, the final belief set, actually corresponds to the labels in the supervised learning. Because labels in artificial neural networks, they tell you what is the goal, like what are the actual true labels about this set of information. So in his work, what is shown is that you can define a certain distance measure that allows us to see that under certain conditions of the network, this distance will become closer and closer to the truth. So we are getting from a belief, from some initial belief set towards the true belief set, closer and closer. And moreover, what is shown in the paper is that this progression of belief sets can actually be modeled with the use of traditionally understood AGM-style operators of revision and contraction. So now to just get back to my original thought, how does it relate to what we've done so far? So again, in this setup, you also have the true state of affairs that is coded by the labels, by the labeled data. What happens in the neural networks, hopefully, is that we are getting closer and closer and closer to that desired KN. So the desired belief set. And the closer and closer might actually happen. So you might get all the way to the desired state, which is actually the same as we would like to have in our setup. But you might get arbitrarily close, maybe never get there, but keep getting closer. And that actually links to an interesting notion of learning that was very strongly argued for by Kevin Kelly some while back. The so-called gradual learning, where we are maybe possibly not getting to the answer and keeping it forever, but rather keeping the distance between our answer and the true state of affairs smaller and smaller. So in any case, this is an advertisement of that particular paper. Please have a look at it so that you see how these things relate. And one of the things that we are looking at now is to bridge between these two perspectives. So to actually make it extremely precise, maybe we have to enrich the notion of identifiability in the limit there. Maybe we have to modify something here, but it's really close. Yes, so for now, I would like to conclude with this. So I talked about learnability understood at truth tracking. We know that the truth tracking will definitely depend on the observation function, so whether or not we have sound and complete data streams. If we do, it can still depend on what kind of revision method we choose. They will not have the same power. Some of them will be really bad at learning. And of course, what matters is the initial plausibility order. Some of the initial plausibility orders will be more rational than others when it comes to the learning task. Then I wanted to outline, because we are here in Women in Logic, that there are interesting consequences for dynamic modal epistemic logic in the paper that I cited, published together with Sonia Smets, Alexandru Baltak, Aibuki Ozgun, and Ana Lucia Vargas. Sandoval. So we have that paper in which we propose a dynamic logic of learning understood in this sense. And that logic actually uses topological semantics. And what I managed to say here about the extra topics is to mention the connection to neural network learning and how belief revision works with that. But I also in the slides leave for you the connection to modeling how bias influences learning. In particular, the different types of anchoring bias, confirmation bias, that are quite common problems in society, but also in different types of formal learning, how they can be modeled with the use of this framework. And also I mentioned some related work on collective learning, in particular a recent paper by authors from the KR community, Richard Booth and Joseph Singleton, about truth tracking with non-expert information sources, where we have a situation in which some of the soundness of the information is actually given up, but instead in their work, there are many agents that can communicate about that state of affairs. And I leave it to you to read the paper and get surprised about how far you can actually push that situation. So yes, thank you very much, Women in Logic. And yeah, I'm very open to some questions, and sorry for running out of time.
Yes, thank you, Nina, for the super interesting presentation. Really, really nice. Thank you very much. There are some questions indeed in the Q&A, and I have also some questions myself. But I'll start with the Q&A. Mirko asks a question on the plausibility orders on worlds. Is the plausibility measured in terms of the number of propositions in the belief sets that are made true or false? Could we put weights on those propositions to indicate which ones are stronger beliefs?
Yes. So I think this question also relates to Elaine's question that is on the bottom. How do you define the distance on belief sets? And yes, it can be done. So actually, I can reveal that in my course, I make students implement belief revision methods, and I leave them with very basic introduction to belief revision, and then they go on and implement belief revising agents. And this is a very common solution to the problem. So they say, in the papers, they actually define some sort of idea that, okay, maybe there could be some propositions could be more important than others. In general, in the literature in belief revision, there is notion of entrenchment that is very crucial, and I encourage you to have a look at that. So this makes certain formulas more important than others because they could be easier to be given up. You know, if there is some really strong underlying belief that governs your whole behavior in life, maybe it's easier to give up some sort of, instead of giving it up, you could maybe try to give up something that is a little bit more contingent, that it's not as important. So there could be a relative importance to different propositions depending, or different formulas depending on how strongly they bind other beliefs together. And that's really studied quite a lot in literature. And of course, there is also a more measurable approach in which we can put certain ranks on possible worlds. And these ranks could be natural numbers, and we can play with that too. That's also a very popular approach in belief revision. Going to Elaine's question, I think it has to do with, towards the end of the presentation, I talked about Theophanis' work about neural networks, and there explicitly in that slide, I can go to that slide here, I actually refer to this distance function, right? So here is the distance function in the theorem. I didn't want to go into details of that, but indeed, the distance of the between the two knowledge sets can be simply taken as the number, like a Hamming distance, version of a Hamming distance. How many propositions are different in both cases? So actually, Theophanis defines two different distance measures of that kind, and he looks into which one is better to model that. But in this case, it would be a version of Hamming distance. Yes, so that would be the answer. What else do we have?
Well, there's another question of Mirko, but there's also, before we go to that one, there's another one related to order of plausibility by Calogne. I'm think you already partly mentioned it, but she said, they ask, is it a way or a function to order the plausibility of possible worlds and how to order them? Is there a way or a function, I think is the question.
Yes. So first of all, you might ask, are, like, for instance, looking at these rationality postulates that I described, the AGM postulates, you might ask, is a certain bunch of rationality postulates of the revision consistent with the existence of such a plausibility order that is, transitive, for instance, right? Or doesn't contain cycles? And that would be the first question. So, like, and that's answered quite extensively in the literature. What type of revision corresponds to the existence of what kind of orders on the space? And other than that, you could use entrenchment, but you could use recency of information, for instance. There could be a lot of arbitrary things to do here. But you see, the problem is that it's just like with subjective probability assessments. I could, because I'm an independent person, I could just decide that I have a completely crazy plausibility assessment to things that I consider possible. Right? In particular, I could even try to violate the general laws of probability. So I could believe in consistent sentences, I could do all sorts of things. But then there are ways to demonstrate that such strange assignments of probability, for instance, would lead me to some undesirable losses, like the book arguments are about that. So they are telling you, you can subjectively assign probabilities, but there are certain limits. Because if you do that, if you start betting on your beliefs, you will keep on losing. Like that's not the way to go. I mean, profit is important. This Dutch book arguments, they go through betting behavior. That's how rationality is proven. And what I'm doing in my work is that instead of looking at rationality through the lenses of payoffs, I'm trying to look at rationality of these plausibility orders through how conducive they are to learning, to the truth. So is it the case that to what extent I can actually order my possible worlds arbitrarily? And what am I risking? Because like some plausibility orders or priors will simply divert me from the truth. They will not allow me to learn as much as possible. So that's the question that's interesting to me, more than the actual constructive ways of saying, okay, this is the way to go. But people do that, and it's a valid question cognitively. Like, for instance, empirically, it's a super interesting question to go out and see how people actually think about plausibility, how people order their possible hypotheses. And it might be irrational, but then who cares, right? I mean, if this is what people do, it's an interesting topic of study.
Okay, thank you, Nina. Another question from Mirko, and that's about the soundness and completeness of data streams. The definition of soundness and completeness is given with respect to a specific state, but then the assumption is given in general terms. Should we assume that such assumption is given with respect to the real world? What happens if the learner does not have such a world in his or her set initially?
Yeah. So we always assume, so that's one of the assumptions of this idealization, is that the real world is accessible. So the real world is an element of the actual state, is the element of the agent's uncertainty space. I have been recently trying to challenge that by looking into awareness notions, where you actually can become more aware of what are the possibilities. So you can expand your set of possibilities somehow. That's just an initial state of affairs. But in general, this is a very common assumption, and I'm not the only one in that, because epistemic logic in general is based on this type of assumption. So if you look at examples like muddy children, for instance, what is simply done is that we take a number of propositions and we list all possible valuations over these propositions, which are possible worlds, and then one of them is the actual one, and then we let agents do something about that space. So, of course, this could be weakened, but that's a question for another talk, perhaps. But when it comes to the soundness and completeness, It's given with respect to a specific state indeed, because it's not given with respect to the specific state. It was used in the definition of learnability with respect to the state in question. But whichever state is the case, so the power of this framework is that whichever of the worlds is the actual world, you would receive sound and complete stream on that world. Right? So it's not like it's favoring one world over others. It's just that it requires of the learner that it's completely, that it's like a general method that independently of which of the hypothesis is true, it will be able to learn it. Right? So in a way, it's not a restrictive assumption. It's actually an assumption that is very, it's a big requirement of the learner to have such an ability. Yeah, this is how I would answer this question for now.
Perfect, thank you. Then Ruba asks a question, belief revision is about updating knowledge bases while preserving consistency. LLMs, on the other hand, often generate outputs that conflict with known facts. Do you see a path where belief revision frameworks could act as a corrective layer on top of LLMs to prevent hallucinations, or even as a guiding principle in their training? And they say, thanks for the interesting talk.
Well, thank you also for the kind words, and thank you for this question. I would absolutely love to see it. I would love to see a little bit more of even tiny symbolic components when we talk about large language models, everything that's happening. Because it's very hard to think of the truth in such setting, right? So imagine, okay, so I don't want to trivialize large language models. They're an amazing tool, and what they collectively, or what they do, is that they take a body of language and they are able to extract the knowledge and the relationships. Actually, it's really impressive what's happening, right? I mean, you can do quite a lot with them. And it reminds me a little bit of this type of consistency theory of truth. So, in philosophy, people struggle with the question of what truth is. And there's this, I think due to Quine, I don't want to lie now because it's been ages since I looked at that, but there's this notion of somehow not caring so much about the truth because it might be inaccessible. We can be skeptics. We might not even believe in the existence of the real world. But what we should worry about is that this space is kind of, the theory is consistent internally, right? So that if everything works well logically, then we are safe. And this is at most as I think large language models can give us, this type of hope that we produced so much knowledge and so much language, is that, as long as we remain consistent to a desirable extent with what we've written so far in our, language, then we'll be fine. The problem is that, of course, anybody can produce any fake news, any piece of false information and throw it into the internet, and just having sufficient amount of this type of information will, of course, skew the whole system. There is no way to connect that. There are some attempts. Actually, one of my students here, Alessandro, he looked into different ways of looking at vectors in these large language models with the hope of actually interpreting something like beliefs in them. So there are attempts, but I don't know well enough what's happening. But I can point, if Ruba, you send me an email, I can point you to the person who might know what to say about that. I myself am skeptical, but I would really love to see that would happen.
Okay, there's still many questions coming in. I do think that at some point we have to maybe, we're going a bit over time, so I'm not sure. What do you say, Agatha?
Let's just select a last question and then.
Okay. Then as last
Mirko
question,
already asked 3 questions, so let's give some other people the chance.
We appreciate the enthusiasm though, Mirko. Then I will go to the question of Anna. Is it possible to extend this to centered possible worlds?
Yes. It's actually very consistent with what I've been talking about. So the spheres, I suppose, Anna, you mean the spheres model? Yes, and I mean, the thing is that it's pretty much a special case of what I've been talking about. The only thing is that the centered spheres, they are well-founded, right? So the assumption there is that there is this center, right? There is the minimum set. And yeah, I mean, it's just throws away a lot of interesting cases for learnability that require this initial non-well-foundedness. But other than that, the way of thinking in terms of pre-orders, it's absolutely consistent with that. So it shouldn't be a problem. I can
sorry. Yeah, sorry. Josephine, read also the last question from Oscar Carvajal.
Yeah, actually, this question was also on my list of questions.
Yes, exactly.
Should I
This
do
is
it?
also what I wanted. Yes, do that.
Okay, real quick
As an
then, Oscar's
exception.
question. Yes, this is the last question we're going to do, though. I'm sure you can email Nina with all your questions afterwards. I mean, yes. So Oscar asks, I'm researching in deontic logic, as are we. From your point of view, could it be possible to apply the believer vision method in this field in order to explain the dynamic between norms? And thanks for the wonderful lecture, Oscar says too.
Thank you very much for the kind words again. The deontic logic. Yeah, so I think some aspects might make sense, but I tend to be quite optimistic about things, so who knows? Maybe I'm wrong. I mean, the framework is quite general. So let's say that we would treat norms as these possible worlds, right? So this points STU. So you could say like, okay, those are the norms, whatever they are, in fact. I don't know, what are they usually in deontic logic? They are formulas, maybe. So that's a little bit tricky. Maybe they're systems, right? So if you find an appropriate way to interpret something as a possible world, then I mean it's super cool, right? I mean you can really use the wealth of modal logics and to talk about knowledge of agents, to talk about multi-agent situation, to talk about what kind of knowledge you can obtain. Yeah, so I would be very interested in seeing this. It's just that the question is there a sensible interpretation of norms as possible worlds? I think there should be, because actually originally I started this research looking at Turing machines. So these points were actually Turing machines or indices of Turing machines that generate a certain set of natural numbers, like for instance. So you could ask the reversed question that is usually asked in computability theory, like given a subset of my set, can I infer what is the hidden Turing machine, the hidden rule of set membership? So I can generalize to next instances, right? If you can see norms this way, then as grammars, for instance, then absolutely, like I see a lot of potential. But how to do it in detail, I have no idea.
Oh, would be interesting
Yeah,
to look into. Yeah, some
very
potential.
much, yes.
Okay. Well, thank you so much again for this super, super nice presentation. And thank you for accepting our invitation.
Yes, thank you so much.
Yeah.
Thank you very much for organizing, for having me, and thank you for coming to the lecture and for this super interesting questions. And please don't hesitate to send me an email if you have more. So, yeah.
Perfect.
Thank you very much.
Great.
Bye.
Yes. And the next Women in Logic seminar is not planned yet, but you will receive an email about that whenever it is, of course. Okay. Have a nice evening, everyone.
Bye.
Bye-bye. Good night.
Bye.
Have a good
Thank
evening.
you. Bye. I will now end the live stream and then end the webinar for everyone. Bye.
Perfect.
Thanks for joining.
Bye-bye.